All right, a little inverse review today. So from a table, how do you figure out the inverse? So I have h of x. So let's figure out what h inverse of x is. So we flip the x and the y. So the y's become the x. So 7 and negative 2 becomes the y. 9 and 0, 6, 1, negative 13, 3, 13, 5. So the x's and the y's, they just get switched. We're going to move on to the next one. So f of x minus 8, we're going to plug in, for f of x, we're going to plug in negative 2, so that becomes negative 10, and then negative 8, then negative 5, then 0, and then when I plug in 11 here, that becomes 3. 11 minus 8 is 3. Okay, what happens in our table? Well, we switch the x and the y, so we get negative 2, 0, 3. The 8 becomes the y. The 11 becomes the y. So if you look at this equation, our y-intercept here, where the x is 0, is 8. And our slope is, let's just do, what's the difference here? That's negative 3. The 0 minus 3, 8 minus 11 is negative 3. So the slope, the change in y over the change in x, is negative 3 over negative 3, which is 1. So this is x plus 8. Okay, we're going to use those functions in a little bit, so keep them handy. Okay. So the general principles that we see for inverse relationships from a table are that the inverses have x and y's that are switched. So something like this, the x's become the y's becomes the x's. And then it's also to remember that, domain and range is also x's and y's. So they also get switched. All right, we're going to sketch the next part of the graph. So we have x minus 8 is f of x. So I have, I'm going to add 1 to make 8. And then the slope is 1. These boxes always trip me up for some reason. I don't know why. On the iPad. Okay, and then x plus 8 is the same thing. So 1, 2, 3, 4, 5, 6, 7, 8. And then a slope of 1. So I'll go back this way. Okay, and what do you notice about the graphs? They are reflective over the line y equals x. It's easier for me to connect them if I have more dots. Okay, so they reflect over y is equal to x. Okay, one test for us is called the horizontal, for inverses, is called the horizontal line test. So I'm going to go ahead and graph my y equals x squared. So I start at 0, 0, over 1 up 1, over 2 up 4. Same symmetrical on the negative side. Okay, so let's go ahead and graph our inverse, which is, let's see, 0, 0 is the same. This is 1, 1, so 1, 1 stays the same. Negative 1, 1 becomes 1, negative 1. Okay. And then this point, right off here. 2, 4 becomes 4, 2. And negative 4, right here, negative 4, 2 is going to be, negative 2, 4 is going to become 4, negative 2. And my graph goes something like this. And what do we notice? Well, the graph is symmetrical over the line y equals x. Okay, so it's reflected over the line y equals x. If I fold the paper right there, the one function will map onto the other. So a test for us is to look at the original function. We're going to look at f of x, and we're going to draw horizontal chopsticks. Okay, so like, does the horizontal chopstick intersect the graph more than once on the same line? So yes, here and here, here and here. So if the function intersects horizontal lines one time only for each line, the function is called 1-to-1 and passes the horizontal line test. It also means that it tells us the function inverse is also a function. So if I look at this graph, it does not pass the horizontal line test because we intersected more than once on one of the lines. So when I look at my red function, my inverse here, is it a function? No, it is not a function. In order to make it a function, we would only graph one part of the line, just the positive part. Okay, but I am not concerned right now about it being a function. Here's what I know about the relationships of horizontal, of graphs for inverse relationships. So the x's and y's are switched, the inverses are reflected over the line y is equal to x, and the domains and the ranges switch. Same thing as an equation. Okay, on to composition. So we talked about this yesterday. In order to prove algebraically how to, if two functions are an inverse, we just compose them. So we're going to take f of x and compose it with f inverse of x. So let's go ahead and start there. We're going to do f of x plus 8. Okay, we're going to plug it into our original here. So x minus 8, we're going to replace x with x plus 8, and that gives us x. Okay, we'll do it for the next. F inverse of x minus 8. Okay, so we're doing f inverse is x plus 8, and we're plugging in x here. That x minus 8 replaces our x, giving us just plain x. When this happens, our functions are inverses because they undo all the operations of each other. Okay, so there you go. When composed, the results will be x. The inverse function undoes the original, and the original undoes the inverse. Okay. Lastly, we're going to talk about how to find inverses algebraically. I think you remember this. Okay. So we're going to switch x and y. So we get x is equal to y cubed minus 4. Then we solve for y, plus 4. So y cubed is equal to x plus 4 cube root, or so we get y is equal to the cube root of x plus 4, or we can say x plus 4 to the 1/3 power. And that's that. Oh, we got to replace. If this is a function, we get to replace this with our function notation. I'm going up this way. G inverse of x is equal to x plus 4 to the 1/3 power. All right, so from the function above, we're going to evaluate G inverse of 23. So G is equal to 23 plus 4 to the 1/3, which is 27 to the 1/3. So the cube root of 27 is 3. 3 times 3 times 3, and that's it. Okay, G inverse of x is equal to 2. So we're going to plug in 2 on the outside, We get x plus 4 is equal to 1/3. To undo the third power, we're going to cube both sides. So I get 8 is equal to x plus 4. And then subtract 4. So x is equal to 4. And we stop.